Press play on an AI-generated video and something quietly final happens. The future is already decided. Every frame, the spray of the waterfall, the bird crossing the sky, all of it was settled the instant the clip was born. You are a spectator. Now imagine the same scene, except you do not press play. You press an arrow key. You want to turn left to walk around that rock and see what is behind it. And the model has no answer because it was never asked what you would do. That gap between watching a future and choosing one is the entire subject of today. Last time we built a video, one fixed block of moving pictures and sound. Today we tear the back wall off that block and step through it. We go from a video you watch to a world you can walk into. And to do that, a machine has to do something genuinely new, invent the next moment of reality live in response to you, and remember everything it has already made. Here is the shift that makes everything click, and it is about the shape of the future. A video model commits to one continuation. It picks a single path through time and paints it. A world model cannot do that because it does not know what you are about to do. So at every single moment, it has to hold many possible futures open at once and collapse them to the one your action selects. Picture a glowing point now, with a fan of faint, ghostly frames spreading out ahead of it. Every ghost is a future that could happen next. You could turn left, turn right, look up, stand still. The model keeps them all latent, all blurry and possible until you move. The instant you press a key, the fan collapses. One branch snaps solid and sharp, the others vanish, and the now point steps forward into it. Then it does the whole thing again. A new fan of futures, another key press, another collapse. Many times a second, forever. A finished clip is a single line drawn through time. A world is a fork that keeps collapsing under your hands. And because it builds each moment from the moment before, including ones it just invented, it has to do this fast enough to feel like you are simply there. There is a second demand, and it is sneakier than the first. Consistency. Look at a wall, look away, look back. The wall has to still be there. Same color, same cracks, same crooked picture frame. Sounds trivial, but for these machines it is brutally hard, and here is why. A normal video never rederives a scene. It already contains every frame. But a world model is inventing the world as you explore it, so when you turn back to that wall, it has to produce it again from scratch and match what it showed you a moment ago. In other words, consistency is memory. To keep a world steady, the model has to remember a world it itself made up. This is the persistence problem, and it is where almost every system today is still weak. Turn away from a table for a few seconds, turn back, and the cup might have drifted, changed color, or quietly vanished. The labs report holding a scene together for, very roughly, up to a minute or so before things start to slip, and even that number is a moving target you should treat with suspicion. So already you can feel the two forces pulling on this whole field. React to you instantly, and remember everything at the same time. Those two demands are at war, and how a system resolves that war turns out to split world models into completely different kinds of machine. Now the single most important idea in this episode, the one that clears up almost all the confusion you will ever read about world models. The phrase world model is overloaded. People use the same two words for at least three genuinely different machines, and they spend most of their time talking past each other. In June 2026, Fei-Fei Li's lab, World Labs, proposed a clean way to cut it by asking one question. What does the machine actually output? Take the same prompt, a kitchen, and watch three different systems handle it. The first outputs pixels. It paints what you would see, gorgeous and convincing, judged purely on whether it looks real. Call it a renderer. The second outputs state. Not a picture, but the actual geometry of the kitchen where every surface is, what you can and cannot walk through, the kind of thing a program, not just an eye, can compute on. Call it a simulator. The third outputs neither pixels nor geometry. It outputs an action. Given what it sees and a goal, it answers, what should I do next, and it never bothers to draw a single sharp frame. Call it a planner. Three machines, one word. Same kitchen, three completely different objects inside, pixels, geometry, and abstract intentions. And one honest caveat. This neat three-way split was drawn by a company that builds the second kind, the simulator, and argues it is the most important. It is a useful map. It is also not a neutral law of physics. Hold it as a framing, not gospel. Start with the renderer because it is the one you have probably seen, and the trick inside it is genuinely clever. Google's Genie is the cleanest example, a system you can give a prompt and then actually steer in real time, around 24 frames a second, holding together for up to roughly a minute. You are not watching a video of a place. You are inside a place the model is dreaming into existence one moment ahead of your controller. Now, the obvious question. To let you steer, surely someone had to train it on tons of video labeled with which button the player pressed. Here is the beautiful part. They did not. The published version learned its controls from raw internet gameplay video that had no labels at all. The trick is called a latent action model. You show the system 2 frames in a row and ask it to figure out, on its own, what changed between them, and to compress that change into one of just a handful of slots, around 8. It is forced to discover that the thing that varies between frames is the controllable thing, without ever being told what a control is. It invents its own little vocabulary of moves, purely by watching. Then, at the moment you actually play, it throws that inference engine away and quietly swaps in your keystrokes where its guessed actions used to go. That is the whole magic. It learned to be steerable from video where nobody was steering. But notice what it never built. There is no map of the kitchen in there, no geometry, only learned habits about which pixels tend to follow which. That is exactly why it forgets, and why, sometimes, you can walk straight through a wall. Now the opposite philosophy. If the renderer's problem is that it has no real world inside, just clever pixel habits, then build the real world. That is the simulator camp, and the clearest example is Marble from the same World Labs. Marble takes the reverse bet. Instead of dreaming up each frame on the fly, it reconstructs an entire three-dimensional scene once, up front, and then lets you roam it like a video game level. The world it builds is made of millions of tiny semi-transparent specks of color floating in space, a representation called Gaussian splatting, plus an invisible collision shell that marks what is solid. And because the scene is now an actual stored object, persistence comes for free. Look away from the table and the cup is still exactly there, not because the model remembered to redraw it, but because it was never undrawn. The geometry simply exists. That is the deep difference. A renderer remembers a world by re-guessing it and hoping it matches. A simulator does not have to remember because the world is just sitting there. But here is a subtle trap you must not fall into. Persistent does not mean physically alive. Marble gives you a world that holds its shape and a collision shell that knows what is solid, but it is, at heart, a beautifully detailed statue. To make a ball actually bounce or water actually flow, you hand that collision shell to a separate physics engine, an old, well-understood piece of software, and let it do the simulating. The world model built the stage. Something else runs the play. Then there is a third camp that throws out the whole premise. Both the renderer and the simulator are obsessed with appearance. One paints pixels, the other builds geometry you can look at. This camp says, why render anything at all? If the point of a world model is to help something act, then you do not need a pretty picture of the future. You need a useful prediction of it. The leading example is a meta system called V-JEPA. Instead of predicting what the next frame will look like, it predicts what the next frame will mean in a compressed, abstract space of its own. It deliberately throws away the unpredictable surface detail, the exact pattern of leaves, a glint of reflection, and keeps only what actually matters for acting: that an object will fall, that a hand will close around a cup, and the payoff is striking. A version trained this way, after just a little general practice watching unlabeled robot video, can be dropped onto a real robot arm and figure out how to move an object from here to there with no training for that specific task. By imagining the abstract consequences of different moves and choosing the one whose predicted outcome best matches the goal. It plans inside its own imagination, in a space made of meaning rather than pixels, and never draws a single frame. This is the camp that the most famous skeptic of today's AI, Yann LeCun, is betting his career on. He left a giant lab to start a company built on exactly this idea, that the road forward is a model that predicts and plans in abstract space, not one that hallucinates ever prettier video. Which brings us to the question everyone actually wants answered. Do these things understand physics? It is the loudest claim in the whole field, and the honest answer is, it depends entirely on which of the three machines you are pointing at, and even then you should be careful. For a renderer, the one that just paints pixels, the evidence is sobering. Researchers built a test called Physics IQ, throwing physical puzzles at the best video models, and the headline finding was blunt. Visual realism does not imply physical understanding. A clip can look utterly photorealistic and still get gravity, fluids, or collisions plain wrong, and how real it looks tells you almost nothing about whether it knows the physics. This is why a renderer can let you stroll through a solid wall. There is no rule in their saying walls are solid, only a memory of how wall pixels usually behave. But in this matters, do not flip to the other extreme and declare these models know zero physics. That same test solves some cases, which hints that genuine physical regularities can be picked up just from watching enough of the world. And the test itself is narrow, a few dozen scenarios scored by comparing pixels, which is a crude ruler for a deep question. So the careful claim is this: a simulator enforces physics on purpose because someone wired in collisions. A renderer picks up a fragile, partial hint of physics by accident, sometimes right, often not. And a planner cares only about the physics that helps it act. When a company calls its flashy video generator a world simulator, treat that as a marketing claim, not a verified fact. Looking real and being right are simply not the same thing. So why is so much money and so much hope suddenly pouring into this? Because of a bet. The loudest version goes like this. Large language models learn the world by reading about it, secondhand in text. But maybe real intelligence has to come from a model of the world itself, of objects in space and cause and effect, the kind of common sense a child gets from crawling around a room. If that is true, world models are not just a fun way to make playable scenes. They are a possible road past the limits of today's chatbots, maybe even a road toward something more general. That is the thesis behind a billion-dollar startup, and behind some of the biggest names in the field changing jobs to chase it. But be clear-eyed. It is a bet, not a result. No system in 2026 has shown anything like broad, reliable common sense about the physical world. It is a serious, well-funded hypothesis with serious skeptics. What is real and genuinely striking is a smaller version of the dream that already works. One lab paired a world that one AI invents with a second AI agent dropped inside it to practice. The agent sets itself tasks, attempts them in the imagined world, learns from what works, and gets measurably better without a single new human example. Train an agent inside worlds another machine dreams up. That loop is the most concrete reason to take all of this seriously, even while the grand claims stay unproven. So let me leave you with the honest shape of where this is and what you now understand. There is a simple rule of thumb for world models in 2026. You can have persistent, real-time, physically exact, and general. Pick 3. No single system gives you all 4 at once. The renderer is real-time and general but drifts and forgets because it builds each moment from its own previous output, and in any loop that feeds on itself, small errors compound. The simulator is persistent and solid, but you reconstruct it up front and bolt the physics on separately. The planner is grounded in action but draws you no world to look at. And the tools to even measure all this are young and disagree with each other. None of that is a wall. It is a frontier, and just a few years ago real-time playable generation did not exist at all. So the honest read is, this is the current chapter, not the final one. But here is what changed for you today. You now know that world model is not one thing. It is three, separated by a single question: what does it output? Pixels, a renderer; geometry, a simulator; actions, a planner. You know why walking into a world is so much harder than watching one. It has to hold every future open and collapse the one you choose, and remember everything it builds. And you know to be skeptical when someone shows you a beautiful clip and calls it understanding. Looking real and being right are not the same thing. The next time a machine invents a world in front of you and hands you the controls, you will know exactly which of the three you are standing inside.